We've looked so far at a couple of models of the atom. We didn't really talk much about the first one, the Dalton model of the atom. That was the solid sphere model, basically where the atom is the atom. They're all different. So you've got the 8-ball and you've got the 3-ball. They're a little bit different. The cue ball, they're a little bit different, right? But they still can't be broken down, right? The 8-ball is still the 8-ball. Okay, there's nothing smaller than the 8-ball or the cue ball or the 3-ball. Then we went to the Thomson model of the atom, which is the plum pudding model of the atom. You've got all these electrons floating around in the sea of positive charge. The chocolate chip cookie dough model of the atom, the harbor model of the atom, sometimes I like to call it, because it kind of reminds us that these, we think of electrons as sailboats, kind of in the harbor in Vancouver, let's say, you know, on a sunny day, floating around in the sea of positive charge. The sailboats would be the electrons, and the water would be the sea of positive charge. Not individuals, just a sea of positive charge. For the first time now, we're going to look at a model of the atom that looks a lot like the model of the atom that we currently have. Okay, this is the Rutherford model of the atom. We call it the planetary model of the atom. Okay, it comes from an experiment that we call the Gold Foil Experiment that was performed by Rutherford and a couple of his assistants, Geiger and Marsden. Looks something like this. And again, it's a bit of a simplification, but something like this. We got a box. We got a box that generates alpha particles. It's not a box of alpha particles. Okay, we didn't collect a whole bunch of alpha particles, stuff them in the box, and put a little hole in it for them to escape. But rather, we had a radioactive material, okay, whatever that was. I'm not even sure what it was. Okay, a radioactive material that would itself decay and generate alpha particles. These alpha particles come out of that little hole. And then they encounter this really, really thin layer of gold foil. Now, when we say thin layer of gold foil, we mean thin. Okay, it's kind of like aluminum foil, except thinner. Okay? You ever seen like gold foil in baking? Like, it sounds odd, but you can actually buy like actual gold to put in baking, like you know, kind of a decorative thing on baking, and you can eat it. It's okay to eat. Ever seen that? Like, it's really, really thin and really light. It has to be, right? Okay, if you're gonna buy it at Michael's to put on your cake or to put on your cupcakes or whatever, I mean, it's not cheap, but it's also not costing you $1,000 to decorate your cake. So it's got to be pretty thin, right? It's got to be pretty thin and pretty light. That's what we've got here, this really, really thin gold foil here. Now, these alpha particles leave this little box here. They hit the gold foil. Surrounding this whole apparatus, we've got a screen that we call a scintillation screen. The scintillation screen will glow just like the screen of the cathode ray tube did. It'll glow when charged particles strike it. So wherever these alpha particles end up hitting the screen, this screen will be caused to glow, and we're going to be able to identify, therefore, where it hits the screen. So Rutherford and his assistants fire these alpha particles one at a time through this gold foil, or at, I should say, this gold foil. And they make 3 observations. Okay, the first observation that they make is that most of these alpha particles, the vast majority of these alpha particles, they go straight through. Well, that's exciting, eh? Boy, that's really exciting after setting up this experiment. Find that, yeah, most of them go straight through. By the way, what does that little 2 plus mean? Okay, we've written alpha like this, right? That's the isotope notation of alpha, 2 protons, 2 neutrons. When I write it as alpha 2 plus, that's not isotope notation. That doesn't tell us how heavy it is or how many neutrons there are or anything like that, right? It just tells us the charge, right? It tells us that there's 2 protons, basically, right? Most of the alpha particles go straight through. We'll see what that means in just a second, why that's important in just a second. Most of the alpha particles go straight through. Now, the second observation that was made was that some of them don't go straight through. Some of them are deflected. They go through. So they go and hit the screen on the other side of the gold foil, but they're not going straight through. Again, most of them are going straight through. So when we say some of them are deflected, like not very many. Like not very many are deflected, but some of them are. The third observation, a few of them, so even less than those that are deflected, a few of them bounce back. So they come back like this and hit the screen over here, or back like this and hit the screen over here. A few of the alpha particles bounce back. So how does this lead to a model of the atom? Let me give you an analogy here. We've got the football field outside. There's, what, 110 yards on the football field. Let's say that we have one person on every yard. So I know there's not yard lines for every yard, but let's say that we've got one person on every yard line. Let's say we blindfold all 110 of those people. And let's say we send all 110 of those people, we line them up, and we send them straight across, one at a time, straight across. Now, the vast majority of those blindfolded people, okay, let's say 100 of them, those blindfolded people, what do they end up doing? They make it right across the football field to the other side. So here's our football field. Okay, here's our yard lines here. Okay, the vast majority of these people that are running across end up running straight across. They make it across and hit the other side exactly what we would expect, still on the yard markers. But a few of those people end up hitting somewhere else on the other side. They don't go straight across. And then a very few of those people, even less than the ones that are deflected, end up coming back, end up bouncing back and coming back to this side. So what does that tell us? What does it tell us? If these guys right here, 1, 2, 3, went straight through, these two guys were deflected, and this guy bounced back. What does that tell us? Well, first of all, it tells us that most of the football field is empty space. Okay, most of these people, 100 of these 110 people, didn't hit anything. They just went straight through. The football field was empty space. So the fact that most of these alpha particles went straight through told us that most of the atom is empty space. Most of the atom is empty space. Now, some of these alpha particles are deflected. Some of these people running across the football field were deflected. What does that tell us? Well, there's got to be something there. Okay, there's got to be something there that's kind of pushing them away. Something's got to be in the middle. It's got to be small because most of it's empty space. And it's got to be positive. Why is it got to be positive? Well, what's going to push away an alpha particle? What's going to push away something that's positive? Something that's positive. So you've got to have something that's small and positive. We're going to call it a nucleus. We got a small, positive nucleus. Now, we're not talking about protons and neutrons yet. We're just talking about a positive nucleus. Few of them bounce back. All right, well, this guy right here bounced back. What do we know about this small, positive nucleus if every once in a while somebody bounces back? Let's put it this way. Okay, if Tanner's the guy who's running across the football field and bounces back, and there's somebody in the middle of the football field that's pushing a couple of these guys away and causing him to bounce back, what we know is that it's not a little 2-year-old. Because if Tanner runs into the 2-year-old, what's going to happen? The poor 2-year-old's going to go flying way the heck over here, right? What do we know about the person in the middle of the football field? Bigger than Tanner. He's big, right? He's heavy, okay? Because if you run into something that's small, then you're going to just knock it out of the way. If you run into something that's big, or sorry, small, but heavy, okay, then you're going to bounce back off of it, right? So that nucleus is heavy or dense. So what do we got here after all of this? This was our model of the atom. A bunch of electrons floating around in a sea of positive charge. Now, this is our model of the atom. We have a small, dense, positive nucleus. Well, there's still electrons. Where are the electrons? They're just orbiting around this small, dense, positively charged nucleus. So why do we call it the planetary model of the atom? Yeah, they orbit around them. It's like the planets orbiting around the sun, right? The electrons orbit around the nucleus. Just like most of the solar system is empty space, right? The planets orbit around this sun, which we think of as being pretty big, but in the grand scheme of things, it's still pretty small, dense, not positive, but small, dense small, dense nucleus with electrons orbiting around it, held in place by an electric force, right? Well, if we think the Rutherford model of the atom, the planetary model of the atom, is more like what we currently accept, then the Bohr model of the atom is even closer. It's still not our current model of the atom, but it's getting closer. Niels Bohr comes along and says, you know, a lot of that stuff that Rutherford said, I kind of like. I can kind of agree with some of that stuff. The idea that there's a nucleus, a small, dense, positively charged nucleus. Yeah, I can go with that. The fact that most of the atom is empty space, yeah, I can go with that. I like that. Okay, it seems to work for me. The fact that the electrons are orbiting around this small, dense, positively charged nucleus, yeah, I can go with that too. So what separates the Bohr model of the atom then from the Rutherford model of the atom? When they both agree that there's a small, dense, positive nucleus, they both agree that most of the atom is empty space, and they both agree that the electrons orbit around. Well, it all has to do with what we call electron levels. The electrons don't just orbit around wherever they want. They don't just go around wherever. It's like, talking about the football field again, okay, it's like the track around the football field. There are lanes on that track. There are 8 lanes, right? The atom essentially has lanes. Electrons have to stay in their lane. There are levels. There are electron levels. Each level is characterized by a certain amount of energy, by a specific energy. So the first level, electrons on the first level have this much energy. Electrons on the second level have that much energy. And on the third level have that much energy. It's kind of like when you go to a hockey game at the Saddledome, there's 3 levels. The people in the first level, they're the guys in suits. They're the guys that show up midway through the first period because they got all the money that they can throw away money. They've got so much money. They don't really care about hockey. They're quiet. They sit there. They eat their snacks and drink their Coke or their beer and just talk quietly to the person next to them the whole time. As you go up to the second level, people get a little bit more energetic, right? They get a little bit louder and they start yelling and cheering a little bit. You get up to the third level, nosebleed section, that's when you get the loud people, the energetic people that have maybe had a Coke or two too many. The higher you go, you get more energetic. Well, each level is characterized by a specific energy. And if you're on the first level, you have this much energy. If you're on the third level, you have a different amount of energy. Now, we're not going to be this, we go to the hockey game. We're not going to be this elitist, you're on this level, you got to stay there. You can move up. You can move levels. That's what I used to do. When I moved to Alberta in 1995, it cost $8 to go to a Flames game and sit in the nosebleed seats, Sport Check Zone. $8. It was cheaper than a movie. Literally, a movie was $9 or $10 at the time. But at that time, maybe 14,000 people would go to a hockey game. So what would you do? Spend $8 and then you move down to the first section, right? You'd make a transition. The electrons can make transitions between levels as well. Okay, I'm actually giving you the third one here. I skipped the second one. The electrons can make transitions as well. They can jump. They can jump to a higher level. When they jump to a higher level, they got to absorb energy to do it. I don't know if you've ever sat in the very top section of the saddle dome. I have. I've sat in the very top row of the saddle dome. Like you feel like you're about 6 miles away from the ice. You know what's worse about than the view of the game? It's getting there. It's walking up there in the first place, especially when you have to walk past people, you know, thinking like, I have better seats than you do. As you walk up to the top. Man, you gotta have some energy in your legs to walk that far because it's a long way up. You have to make sure you've eaten your Wheaties in the morning or drank your Red Bull before you go to the game in order to get to the top level. You need to absorb energy. The electrons need to absorb energy as well to go to higher levels, to jump to higher levels. And usually the energy they absorb, usually, is in the form of electromagnetic radiation. So we absorb an infrared photon or a visible light photon or a ultraviolet photon, and the electron will jump to a higher level. The electrons can also fall to a lower level. They give off EMR. Good. They give off EMR in that process. Remember when we introduced the concept of EMR ages ago now, like a month or so ago now? Very first day, we said that there were 3 types of EMR, infrared, visible light, and ultraviolet, that were produced by transitions of electrons in atoms. These are the transitions. Okay, when an electron falls from a high level to a low level, gives off EMR. Hey, let's say I'm in the third deck of the saddle room, and I'm looking down there during the first period, and I see these 2 seats that are empty the whole first period, and I decide I'm going to move down. Okay? As I get out of my seat, somebody trips me, and I'm tumbling down the stairs. What happens? I scream like a little girl. I give off EMR, I give off energy, sound energy, but kind of analogous, right? As I go down, I scream. Maybe I scream in delight. Hey, I get $200 seats. I only paid $30. I give off energy as I go to a lower level. I absorb energy as I go to a higher level. I give it off as I go to a lower level. Okay. Now, the second one, which we skipped past already, it's kind of the hardest one, actually. The second one says that the electrons exist on what we call stationary states. Well, what does that mean? As the electrons orbit around the nucleus, I'll use my keys as an example here. As the electrons orbit around the nucleus, they accelerate. It doesn't mean that they speed up or slow down, but they accelerate because they're changing direction. What kind of acceleration do they experience as they orbit around in this circle? Centripetal acceleration. What did Maxwell say accelerating charged particles do? Accelerating charged particles always produce EMR. Okay, so these electrons, as they orbit around the nucleus, should produce EMR. They don't, though. In this case, they don't produce EMR. Okay? They produce EMR when they make a transition, but not as they accelerate in a circle around the nucleus. It's like they're not moving. It's like they're not accelerating. Okay, it's as if they're not accelerating. It's as if they're standing still. It's as if the electron is right here. It's as if the electron is Stationary. We call it a stationary state because these electrons, it's like they're exempt from the laws of electromagnetism. They don't produce EMR as they accelerate around the nucleus. Now, we can produce EMR, but we got to have a transition to do that, not simply by accelerating around the nucleus in that circle. Does that kind of make sense? Kinda, like, I mean, at a fundamental level, it probably shouldn't make sense. Okay, but general idea hopefully does make sense to us. Good. Let's look at one more little aspect of the Bohr model, and then we'll continue on with the Bohr model tomorrow. This is where we're going to wrap it up here today. Maybe even have a couple minutes to work on those practice problems for homework. We got 3 pictures here. Let's take a look at the first one. We got a light bulb over here on the left-hand side. Okay, a light bulb. Okay, an incandescent light bulb, not a fluorescent light bulb, but an incandescent light bulb. Okay, it's a heated solid, right? A filament of a light bulb, or it could be a heated liquid, or it could even be a gas under high pressure. It produces EMR. In fact, it produces what we call white light, which is a combination of all the colors. It produces the rainbow, the continuous spectrum. We saw that term on our test, right? The continuous spectrum. I explained what that meant. Okay, it's when one color transitions into the next color, not specific lines. But we don't see it as a continuous spectrum. When you look at your light bulb, flip on the light when you go home tonight, okay, you don't see it as a rainbow. You see it as yellow or white light emanating from it or coming from it. But if we stick a diffraction grating, or what else could we stick in there? A what? A diffraction grating or a prism. Doesn't really matter. The prism will produce Roy G. Biv. The diffraction grating will produce the opposite to that, right? Okay, then it breaks the color up. Then it breaks the white light up. This doesn't really have anything to do with atomic transitions right now. This is just serving as kind of a base, kind of a reference diagram here, okay? Okay, when we have a solid, a liquid, or a heated solid, a heated liquid, or a heated gas under high pressure, and then we stick a diffraction grating or a prism in front of it, this is what we get. But now, let's take that hot gas and put it under low pressure. It still produces a whole bunch of different colors of light. But this time it produces those colors of light as a result of electron transitions. It's hot. What happens? The electrons fall to lower levels. They go down to lower levels, and as they do that, they give off EMR. Okay, when we see that EMR, that's what's happening right now in these light bulbs, these fluorescent light bulbs. It's producing various colors, but not a continuous spectrum. It's not producing all the colors of the rainbow, transitioning from one into the other. It's producing distinct colors, but they're coming out combined. So we see it still more or less as white light. But if we were to put a prism or diffraction grating in front of this, we wouldn't see it forming a continuous spectrum. We'd see it forming lines. Here's a red line corresponding to one transition that electrons have made within that light bulb or whatever. There's a yellow line corresponding to another transition. A couple green lines corresponding to 2 more transitions, blue, indigo, and violet, corresponding to these different transitions that electrons have made. Does that make sense? When we have these atomic transitions going from high levels to low levels, we call it an emission spectrum. We see bright lines. Now let's take a look at the third diagram. Let's get rid of the cold gas for a second in the third diagram. If we get rid of the cold gas, and then here, let's cover up this too. If we get rid of the cold gas, what do we got? We got the same thing as our first diagram, right? We got a continuous spectrum, which has nothing really to do with atomic transitions. Okay, we got a continuous spectrum. But as soon as we introduce that cold gas, what do you think that cold gas does? Yeah, it absorbs photons. And as it absorbs photons, electrons will jump to higher levels. So what do we get over here? Well, we get the continuous spectrum minus whatever photons were absorbed. Tell me what photons were absorbed here. Well, there was a red photon absorbed because you have a continuous spectrum except for the red photon. There was a yellow absorbed because you got the continuous spectrum, but you're missing the yellow. A couple green ones were absorbed. Blue, indigo, and violet were absorbed. So we get an emission spectrum when electrons make transitions from high to low levels in a hot gas under low pressure. We get an absorption spectrum when we absorb photons by a cold gas. Travis? Would the gas itself be changing color? No. What you get is light coming out of the gas. Yeah, it would. Yeah. But not. I mean, not to the point where. Not to the point where it would all of a sudden reverse. All right. These are the exact opposite, right? Okay, so that's obviously the big difference. The electrons are jumping in the first one. They're falling in the second one. What do these two things have in common, though? Yeah, for sure. There's transitions, opposite transitions, but still transitions. Take a look at the pictures here. What do you notice about those two spectra, besides the fact that they're, one's absorption, one's emission? The lines are in the same spot. So what does that tell you about whatever element this is compared to this element? It's the same element. One of the big things about this is that one of the big applications of this is identifying unknown materials. Right? We can identify unknown gases by simply looking at the spectrum. I had a professor in university. This is what he did. He took pictures. He took photographs of atomic spectra, different elements and molecules, and he published them. That's what he did. That was his whole academic career, is publishing, doing studies of atomic spectra and publishing pictures. He was also kind of an amateur astronomer, just not part of his job, but just because it was kind of a hobby. And I think he realized, because he loved astronomy, how useful something like this was. You see this star. Hey, this star, never seen it before. Nobody's ever discovered this star before. Okay, Brendan's looking up in the sky in a telescope, and he discovers something that nobody's ever discovered before, which, by the way, does happen sometimes with young people. Like, that's one of the discoveries that can be made by untrained people, is discoveries of stars that nobody else has ever observed before. So Brendan's observing this. He brings it to the attention of the astronomy department at the U of C, and they say, hey, that's great. Nobody's ever seen that before. And they say, well, we should find out what it's made out of. We should find out what this star is made out of. Let's take a look at the light that it produces. Let's take a look at what the spectrum looks like, the emission spectrum looks like. And then let's compare it with the photographs that were taken by Mr. Dickie's professor, or the photographs that were taken by this other person, and identify what that star is made up of. If it looks the same as the photograph that was taken in 1994 by whoever, then that star must be made up of the same material that that photograph was of. Does that make sense? One quick example, and then we're done. Okay. We get three. This was an actual diploma exam question, by the way. Now, though, it's probably 10 years old, or even a little bit more now. If you saw this now, it would be in color. They usually give you one or two color diagrams in the book right now, which kind of makes me think, like, well, geez, if they're going to put color in a couple pages, like, why don't they just, a couple pictures, why don't they just put color through the whole thing and at least make it a little bit more exciting for us? This would be in color now. We see a hydrogen spectrum that maybe, somebody has taken a picture of. Okay? Maybe you see another helium spectrum. What do you notice about hydrogen and helium? They're different, right? As we would expect. And then sodium is different again. Then we have this unknown gas mixture here. I'm going to give you 30 seconds to determine what element or elements are present in this unknown gas mixture. This is what we're observing through our telescope. Okay? This is what we know already. Okay? What's the composition of that star? Travis thinks it's hydrogen and sodium. Why do you say that, Travis? Because it has the same ones, okay? Same lines. All right, so that's hydrogen. Are all the lines for hydrogen there? Yeah, they're all there, right? What about sodium? Yeah, there's only 2 of them, and they're both there, right? What about helium? Hey, this one's here for helium. This one looks like it's here, pretty close, right? Is helium there too, or at least a little bit of helium? No. Okay, no, you're right, Travis. It's hydrogen and sodium. All the lines for the spectrum have to be there in the unknown gas mixture. Okay? So conclusively, we can say hydrogen and sodium are present there. All right? Good? Excellent. That's it for today.